Can someone please confirm if my screen is visible?
Yeah, it's visible.
Is everyone there? Should we start? Is there anyone left to come? Gustav, you can click on the comments button option to check to read the comments. If you didn't know. If you didn't know.
Pardon, I couldn't hear you.
I was saying you can click on the comments option there.
Uh-huh.
If you didn't know, like people usually ask doubts there.
Okay. Okay, we are starting the session. Everyone, welcome to the motion planning session. I am Kaustubh and me and Joshua will be taking this session. I will be covering the introductory part where I will be covering the search-based methods, and Joshua will tomorrow cover some advanced topics. So let's see. So in an autonomous vehicle, this is the decision-making hierarchy that is generally followed. First is the route planning, where we give the starting destination and the starting location and the destination to the system, and a route is planned in the map given. Then comes the behavior decision making part where the route that is generated, the vehicle has to navigate through that route. And for that, certain decisions need to be made, like following traffic rules and or overtaking other vehicles or uh, stopping when signals arrive and all those things. So the behavioral decision making part makes decisions, and it provides those decisions to the motion planning section. The motion planning takes this decision and transforms them into trajectories that the vehicle can follow. The trajectories, or by trajectories, I mean also the velocities at that point of time which the vehicle needs to follow so that it is also comfortable for the passengers of the vehicle. And this trajectory is then passed to the vehicle control section, which then uh, makes sure the vehicle follows those commands. So I will be covering the route planning section today, and Joshua will be covering the behavioral decision making and motion planning part, and we will be covering the vehicle control part. So the graph search for the route planning section, we generally use graph search algorithms for finding shortest paths between 2 points. Now, in these algorithms, we generally take a graph, start and an end location as input, and the algorithm returns the shortest path if one exists between the 2 points. In the real world scenario, we can treat different locations on the map as nodes in the graph and the roads connecting them as edges. And we use that graph to find the shortest distance. So one example would be Google Map, where we provide our destination, it gives us the shortest path. Now, two important functions are used in graph search algorithms. So like one is the heuristic function. The heuristic function tells us that from the current node, what is the estimated cost of reaching the destination node. This is the HN is generally an underestimate or equal to the actual cost of reaching the uh, uh, destination node. Because if it is higher than the actual cost, it might not result in giving us the shortest path. We will look into this part more when we will be covering A-star search. And another is GN. GN tells us the cost of reaching the current node from the start node. And for all the search algorithms, we sum these two functions GN plus HN, and we call it SN, and we store the nodes that we will visit and their F values in an ascending order in a priority queue. So this is a basic algorithm for search methods. So we first start with an empty priority queue. We set our current node as the start node, and then we visit all the adjacent nodes from the current node. And once we visit the adjacent nodes, we push them in the queue along with their F values. Later, we will find out that for different algorithms, just changing the G function and the H function will result in different types of output. So I've here given a very generalized algorithm, but if you look at books, the algorithm will change depending on the search algorithm you are using. Now, once you have inserted the nodes in the queue, you sort the queue in ascending order of the f values, and after you've visited all the adjacent nodes from the current node, you mark the current node as visited, and you pick the first element from the queue, which is the one having the lowest f value, and again you repeat the process. You visit all the adjacent nodes from that node and insert them in the queue, and so on. If we continue this until the current node is the goal node, and once the goal node is there, we backtrack from there to get the shortest path. So breadth first search. Breadth first search is the most basic graph search method. Here we won't really consider the heuristic function, so hn will be 0, and for the gn, that is the cost of reaching a particular node from the start node, it is the same for every node. That is, we also do not consider this. So when we are inserting a node in the queue, since all of them have the same g values, which in result gives them the same f values, the priority queue acts like a normal queue, that is first in, first out. So the first, from a current node, the first adjacent node that we visit is pushed in the queue, and after all the adjacent nodes are visited from the current node, we pick the first visited node and then visit all its adjacent nodes, and we go on like the problem with this is, since we do not consider the cost of reaching that node from the start node, we will although get the shortest path, but it might not be the most optimal path, because in real world scenarios, suppose the shortest path is a road in a very bad condition, and it might traveling through that road might damage our car. So to take this into account, we introduce the cost of reaching a particular node from the start node, which is GN. And we do this using the Dijkstra's algorithm. Here, the GN varies for every node, but again, we do not consider the heuristic function here, that so HN remains 0. Now, from the start node, once we reach the adjacent node, we push them into the queue and sort the queue in terms of the f values. Here, since we are considering GN, which varies from node to node, the f values will also be changing, and so after visiting all the adjacent nodes from the current node, we will pick the node with the smallest f value. That is the node that is closest to our current node, and we will keep going on like this. Dijkstra's algorithm also gives us the shortest path, but this time it gives us the path with the least cost. The problem with these two algorithms is that the search space, when we are searching for the shortest path, the search space expands in all directions. So once we have covered the entire search space from the start node, we can get the shortest path to any nodes, which is a good thing. But often in real world scenarios, we don't really need this. So when we're doing this, we are wasting time. So to account for this, we introduce the heuristic function in the next algorithm. And here is a video of how the breadth expands. So as you can see, the green node is our current node. And when we start, first it checks its two adjacent nodes. It puts them in the queue. Since we do not consider, since for all the nodes, the G values are the same, so the queue acts like the first in, first out normal queue. So first, then we will take the first visited adjacent node. So the current node shifts to there, and again we see its adjacent node and puts them in the queue, and then we move to the next adjacent node we visited from the first node. And as you see, it keeps on proceeding like this. It will cover the entire thing. So now coming to A star search algorithm. As I mentioned, the disadvantages of a breadth first search and Dijkstra's algorithm, those are solved using A star search algorithm. So we do not, the search space do not expand in all the direction, but it is a very directed search. To make this possible, we use the heuristic function. As I mentioned before, the heuristic function is just an estimate of the cost of reaching the destination node from the current node. We can do this, we can either take the Euclidean distance or the Manhattan distance or any other way, but we need to always make sure that Hn is an underestimate instead of an overestimate. That is, Hn should never be more than the actual cost of reaching the destination node. So in case Hn is more than the actual cost of reaching the destination node, what will happen is, suppose for the shortest path, we consider Hn more. Then, and for a path that is not the shortest and optimal, its Hn is less than the overestimated Hn of the shortest path. Then we won't consider the shortest path, but the non-optimal path, which will not give us the best result. So, which is why this condition must always be satisfied. And here the priority queue is again sorted in ascending order of the f values, and so it always proceeds in the direction of both of the nodes which are both closest to the starting node and also closest to the destination node, and that's why it is directed towards that part. And this gives us the most optimal path to the goal in a very short time. The problem with those search algorithms is that we always need a graph to make them work. But in certain scenarios, we won't be given a graph. For example, navigating between 2 points in a parking lot. Here, we don't really have a graph. So how do we find the shortest path to navigate from one point to another point in the parking lot? For this, what we generally do is if we know the configuration space, we create a graph in that space and then find the paths using that graph. Now, generally, these are two separate problems and these are generally solved by two separate algorithms. But rapidly exploding random trees is one of the algorithms that solves this, is one algorithm that solves both these problems. So here we start with a graph with just a single node, that is the start node. Then at any random point in the configuration space, we create a node. First, we check if the node lies in any obstacle. If it lies in any obstacle, we don't consider that node, but we again create a random node. If it does not lie in any obstacle, we find a node in the graph which is the closest to that node. Since we are just starting, there is only one node, it will be the starting node. And now we check if the distance between our closest node and the random generated node is less than delta. So delta is just a factor we consider so that we don't really create much bigger edges, but reasonable length edges. If the distance is less than delta, we consider the randomly generated node and connect them with the closest node in the graph, and the graph now consists of the random generated node as well. However, if the distance is greater than delta, what we do is we create another node which is at a distance delta along the line connecting these two nodes. And we use that node instead of the randomly generated node. And then again, we put that node inside the graph as well. And this process is repeated until we reach the goal location. So this is an example. Suppose we have an existing graph like this. Now we create a randomly generated node, which is marked as red, and we find that the closest node in the graph is here. It is also marked, as you can see. Now we find the distance between these two. As we can see, the distance is greater than delta, so we create another node on that line, which is at a distance delta between these two nodes, and we consider this node instead of the randomly generated node, connects it with the graph. This way, the entire graph and the path generates towards our goal. Now, if we sample the randomly generated nodes uniformly, the tree will grow in all directions. However, to make sure the tree proceeds in towards our goal direction, we need to increase the probability of sampling the nodes towards our goal state. Goal state. That way, it will proceed faster towards the goal. And this is a video of how RRT expands. In this case, I have used and uniform sampling to randomly generate the nodes. As you can see, it proceeds in all the directions instead of any particular direction. And this covers the search-based methods. So this is all for today's session. If anyone has any questions, they can ask. Most of you already do most of the search-based methods, and RRT is something new, I believe. If nobody has any questions, then the session is over today. Tomorrow, Joshua will be taking the session. He will probably be talking about the Bernstein polynomials and trajectory optimization using that. So, thank you.